Very good. Okay, so today, logistic growth, 8H. And what we'll begin by talking about, just on the left-hand side of our notes page, on page 20 there, we have what the logistic model is. So in methods, we touch on it when we're talking about applications of calculus, and we just talk about that it's a kind of a model that frequently pops up, particularly when we're modeling things like the height of a tree. Okay, so like if you've got a tree growing, it grows quickly and then it starts to slow down, and it approaches this limiting value. We have this horizontal asymptote, of which a tree doesn't tend to grow taller than a certain amount, okay? We also have it for like modeling populations, like if you have some biological population living in an area, it's going to approach some limiting value because of competition for resources and amongst one another and so forth. So logistic growth, and we also do have logistic decay when it comes in the opposite direction. And I've just listed there with the dot points, we've got a number of properties that these functions have. So we've got the form that it takes, where the asymptote occurs, where the point of inflection occurs. And what is a point of inflection, right? That we have the rate at which it's changing is increasing, and then the rate at which it's changing is decreasing. Okay, so although the function is increasing, the rate at which it's increasing is decreasing. Okay, so that just means the slope's getting smaller as the x value increases. Then we have along underneath, we have the general proof for the logistic function. And that's the kind of algebra we're going to be performing, but in each specific circumstance. So let's get into our first one here, where we have the rate of population growth since the year 2000 can be modeled by this equation. So we have dn on dt, the rate at which n is the population of the world in billions, and t is in time, years since the year 2000. And we've got 0.002 n multiplied by 12.5 take n, all on top of 12.5. Okay, so this is a differential equation that describes the rate. Part A, show that this is true. Okay, show that. Now I'm going to just start with the right-hand side. So make our argument. Right-hand side is this, 1 on n plus 1 on 12.5 take n. Okay, cross multiply. Equals 12.5 on top of n times 12.5. Okay, we're familiar with those, we've been doing those a fair bit. Start with where you can cross multiply and then bring them together over the same denominator and simplify. Okay, part B. Hence, solve the differential equation to show that the population is this. So this is an old exam question, right? And this is how they set them up. Part A, show this. Part B, show that the differential equation solution is this. So we're going to perform the integration, and we're going to solve through for the function n. So we're going to solve this differential equation. So the first thing I'm going to do is I'm looking here. We're going to perform substitution with what we've done above. I'm going to try and isolate the number by itself. So I'm going to multiply both sides by 12.5 on top of n times 12.5 take n. Okay, so I'm moving all of the variables to the left-hand side. Okay, and you can see if I multiply both sides by it, that's going to cancel on the left-hand side, and that's going to cancel. We'll just be left with this 0.02. So over here, we're going to have 12.5 on top of n times 12.5 take n, dn on dt, and that's equal to 0.002. Okay, so that's our first step. And now we're solving these integration equations, right? We're going to integrate both sides with regards to t. Okay, so I'll write that out. Integral of 12.5 on n times 12.5 take n. dn on dt with regards to t. And that's going to equal over here the integral of 0.002 with regards to t. Cancel. And so we're required to integrate this with regards to n And when we're looking at that, we go, well, we don't know how to integrate that. That's quite a complex function. We have some product going on at the bottom here, you know, we've got an n squared term. However, whenever it says hence do this, we're always using what we've shown above. And above we showed that what we have on the left-hand side is equal to this part on the right-hand side. And we can integrate both of those components separately rather than this combined component. So I'm going to first split it up. Okay, I'm going to perform the substitution. 12.5 on n times 12.5 take n is equal to this. So let's write that up here. Perform our substitution. So 1 on n plus 1 on 12.5 take n with regards to n. Okay, that's what's going on the left-hand side. And on the right-hand side, you can evaluate this at every stage. Okay, let's integrate both sides then. All right, so on the left-hand side, integrating with regard 1 on n with regards to n, that's going to give us ln modulus of n. And here we have 1 on ax plus b. Okay, so we can think about it like, if we have 1 on ax plus b, the integral is 1 on a ln modulus ax plus b. All right, where the a value is the coefficient of the variable. So in this circumstance, the a value is -1. So we're going to have 1 on -1. So that's going to give us that negative ln modulus ax plus b. That's a decimal, by the way, 12.5 seconds. Okay, so that's how we're getting that negative there on the left-hand side. And on the right-hand side, we're just going to have 0.002 plus c. Now, we're not going to e both sides yet, because when you e, you apply it to the whole side. Instead, we're going to collect this to a single logarithm. All right, so we know ln a take ln b. That's going to simplify to ln of a on top of b. All right, we'll leave the right-hand side as it is for now.
Do you need a t with the 0.002?
Yes. Thank you. All right, now we'll apply e to the power of both sides. So we've got, we're going to get rid of our ln. So we're going to have here n on 12.5 take n. And because it's modulus, we're going to get our plus or minus here, aren't we? Plus or minus, so we have e to the plus or minus c, no, we'll do that after. Let's keep the modulus on it now. We'll have e to the 0.002t plus c, and now we'll split the modulus. N on 12.5 take n equals plus or minus e to the c, e to the 0.002t. Okay, we're getting there. There's a bit more involved. Okay, what we're going to do next is we're going to reciprocal both sides, because when we get to a stage like this, we're trying to solve for n, and there's not an immediate solution, but we're going to show you a cool trick here, what we're going to do on the left-hand side. So what we're technically doing is we're raising both sides to the power of -1, okay? And what that allows us to do is flip the fraction on the left-hand side. So on the left-hand side, we're now going to have 12.5 take n on top of n. And on the right-hand side, all we're doing is ending up with a negative power on our e terms. So we have e to the negative c, and we have plus or minus, and we have e to the negative 0.002t. All right, we're getting there. Okay, next we're going to split the denominator on the left-hand side. So it's a bit like saying if we have 3 take x on top of 2, we can split that as 3 on 2 take x on 2. Okay, that the denominator belongs to both terms. Often when we're combining fractions, we go, yep, they have the same denominator, so we can express it over the same denominator. We're going the opposite way for the purpose of simplification. So we have 12.5 on n, take away n on n. N on n. And on this side, we'll keep it as plus or minus e to the c, negative c for now. We'll solve that through in a moment. Okay. n divided by n is 1. All right, we're almost there. Okay, plus 1 to both sides. Plus 1. And then what we're going to do is swap these components. Okay, so we're going to have 12.5 on top of our. Now's when I might perform the a substitution as well. A e to the negative 0.002t plus 1 equals n, where a is plus or minus e to the negative c. Okay, cool, like some awesome algebra there, right? But we've actually got one more thing to do, which is solve for a, which we haven't done yet. So is everyone okay if I clear a bit of space?
Yeah.
You won't need much. So we're going to use that equation because we know that n is 6.08. Remember, n is in billions. N is 6.08 when t is 0. All right, so we're going to have 6.08 equals 12.5 on top of a. We don't know the value of a. E to the negative 0.00, that's going to be 0 because it's the time value is 0 when initially at the year 2000 when time is 0. So we have here e to the power of 0 and then we have a plus 1. So e to the power of 0, well that's just 1. All right, now we're solving through here for a. Okay, so what I'm going to do is I'm going to swap a plus 1 and 6.08. And then subtract 1 from both sides. What is that about? What it tells us, 1.06. Nice. Very good. So we've demonstrated the truth that the differential equation, the solution to the differential equation, the particular solution is 12.5 on top of 1 plus 1.06 e to the negative 0.002t. All right, cool. Let's move on to part C. According to the model, in what year is the population growing at the fastest rate? So this is a logistic model, all right? And what we'll try and do maybe is compare it with what we have on the left-hand side of the page. So we've got 12.5 on top of 1 plus 1.06 e to the negative 0.002t. And that's the number of people. Now, I think there's two ways you can do this, all right? Now, the first thing is to understand the maximum rate of change will always be a point of inflection. Okay, that's a methods technique. We understand that the function is steepest, again if I provide the graph of it here, the function is steepest when it changes shape from concave up to concave down. That's when it's steepest, that's when it's a point of inflection. So if you were to do that using what you currently know, you would graph this function, graph its derivative or its second
Emily
derivative.
Massey to the library immediately, please. Emily Massey to the library immediately, please.
So graph the function and its derivative and G-solve the roots of its second derivative or the maximum turning points of its first derivative. All right, so if you're not sure, I can show you that. Otherwise, let's look at what are the properties of a logistic model. So particularly the third dot point. There is an inflection point when y equals c on top of 2, where c is the number we have at the top. C is the limiting value. The limiting value here for the Earth's population is 12.5 billion based off of this model. So that means the point of inflection occurs when y equals 12.5 on top of 2, that's 6.25. So we've got a y value for when it occurs, all right, but our question is, when does it occur? What is the x value? What is the time value when the point of inflection occurs? So we know the y value is 6.5. What we'll do, we'll graph this function, and we're going to g-solve the corresponding x value. Okay, I'll do that in a moment so that we can answer, I'll do that right now. And the answer to part B, the limiting value, the one that it approaches is 12.5 billion. Okay, that's the asymptote. The horizontal asymptote is 12.5. That's the value that the function approaches. All right, so shall I just evaluate that one quickly? $12.5 on top of 1 plus 1.06 e negative 0.002 x. What is going on? Negative 0.002, 1 plus 1.06, 6 b. Oh wait.
Coming early. It's a third.
Oh, sorry, I'm changing the y max. I should be changing the x max. Sorry. A couple of zeros in there. There we go. That's a bit better. Alright, now we want to know when x value, y is 6.25. So g-solve, x calc, when y is 6.25, my x value is 29. Okay, now, my t value I should say, 29.13. So that's an appropriate answer, 29.13. 29.13 years after the year 2000, that's going to be 2029. It's coming up. Okay. Now, would you like to have a go at the next one by yourself, or do you want me to go through it with you? It's a pretty similar process.
We'll give it a crack.
Give it a crack.
Sure, we can try.
Excellent. Give it a crack, and when you get stuck, if you get stuck, I should say,